So from the pre-lesson investigation, we should have seen that the parent function of a linear absolute value function and it looks like y equals absolute value of x. No bells and whistles, no pluses and minuses. If you have just a basic function with just an x in it, we call it a parent function. We should have seen that it looks something like this. And I'm going to freehand this because I can't draw it perfectly with preform shapes. So we should have seen that it looks something like a perfect V. And that sort of should make sense because if you think about what a regular line does, if you look at, so I'm going to change colors. This is sort of scratch work on the side here. If you remember what y equals x looks like, y equals x looks something like this. Blah. I'll freehand this too. Y equals x looks something like that. And what absolute value does is it forces everything to be positive. So this guy here, this part of the graph is what's below the x-axis. Those are the negative bits. So all the absolute value does is it just swings it up top to make it positive, giving us this V shape here. Now, how to sketch these V shapes? Yeah, we could do the tried and true fashion of XY graphs, right? XY tables. To graph, we can do this all day long, but that's a pain in the butt. What the pre-lesson investigation had you do was exploring function transformations. So this is the observations that you should have gotten from the pre-lesson investigation. For the graph of any function, y equals f of x, we saw that if you take a function and add anything to it, so I'm using the letter C to stand for any number, constant, that shifts the graph up by exactly that amount. So if I add 2 to a function, it moves the graph up by 2. If I add 1.7 to a function, it moves it up by 1.7. We saw the exact opposite thing happening when we subtracted. That shifts the graph down. Another observation or interesting thing we should have saw is that when we do the adding subtracting inside the absolute value directly to the x, it sort of didn't happen or didn't behave the way we expected. When you add directly to the x, it actually moved things to the left. And when you subtracted, it moved things to the right. So when you do stuff to the x, it's sort of backwards to what you think it should happen. And the last transformation that we looked at, these aren't the only ones, but these are the ones that we only looked at, was when you multiplied a function by a number. So if I took a graph and multiplied by a number, specifically, if that number was bigger than 1, it sort of stretched it vertically or narrowed. So doing c times f of x, where c is greater than 1, vertically stretches or narrows by the factor of whatever you multiply by. So if I multiply by 2, it will vertically stretch the graph by 2. If I multiply it by 1.7, it will vertically stretch the graph by 1.7. We saw it get very, very skinny. We saw that if we multiply by numbers smaller than 1 but kept it positive, we saw it sort of shrinking or flattening or widening by the same factor. Right. So if I multiply by 1/2, I made the graph vertically flat by 1/2. If I multiply by 0.2, I vertically flattened or widened by a factor of 0.2. And lastly, we saw that if we multiply by a negative number, it flipped the graph vertically. The technical term is it performs a reflection across the x-axis. But informally, we saw that it flipped. This entire list, there's more to it, but we'll talk about the rest some other time. This entire list of function transformations is probably one of the important things to know in mathematics, because notice the definition, it says it's for the graph of any functions. We're only looking at absolute value functions today, but we'll be using these transformations over and over and over in Algebra 2. So how can I use this idea to graph a complicated looking absolute value function without having to make a cumbersome XY table? Well, let's talk about the parts of an absolute value function again. I'll do it really quickly. So we saw that the basic parent function, absolute value, looked like a V. The very, very tip or the point we call the vertex. And each one of these guys here, I guess I should do a different color. Each of these guys here is what I call branches. Well, to sketch an absolute value function then, therefore, all you have to do is to be able to read the transformations that are present, and then you go ahead and move the vertex to whatever the instructions tell you to do. For example, if I ask you to sketch y equals, I don't know, absolute value of I don't know. What are the what? Branches. Yep. Say 2 absolute value of x minus 3 plus 1, say. All we have to do is be able to read the transformations. So the minus 3, if I recall the list above, tells me to go right 3. The plus 1 tells me to go up 1. And the 2 is my vertical stretch. Now for linear functions, that is your slope. Notice I put slope in quotes because it really isn't your slope, but we can think of it as your slope. You're done. You can generate a pretty decent graph now. So go ahead and make a coordinate system. And then all you got to do is listen to your instructions. So you know how an absolute value function looks like a V? An absolute value function starts at the origin, 0, 0. what you're going to do is just listen to your function transformations, up, down, left, right. It says right 3, up 1. So guess where your new vertex is? Right 3, up 1. And then that vertical stretch of 2 is your new, quote, slope. Slope of 2 tells you go up 2 over 1. So from this point, I'm going to go up 2 over 1. Up 2 over 1. All you have to remember is that this is an absolute value function. And what shape does an absolute value function look like? A V. So you just have to do the slope in the other direction. Up to left 1. Up to left 1. There is our function. That is our graph. That's it. We graphed it. Easy peasy. Questions, comments, concerns? Let's just do one more to make sure that we know what the heck we're doing. Suppose I ask you to sketch f of x equals negative 1/2 absolute value of x plus 4 plus 2. The first thing we have to do is read the transformation. So just go ahead and shout it out loud. What transformations do you see in this equation? Up, down, left, right. I hear an up 2, left 4. That's it. That negative 1/2, that's multiplying, that is your, quote, slope. So this is your slope. So then that's the hard work, which is not hard at all. All you got to do now is graph it. Draw a coordinate plane. I'll draw my tick marks. Listen to my transformations. Left 4, up 2. It will be upside down. And then once I have my vertex, I'll listen to my slope. Because my slope is negative, instead of going up, I'm going to go down. So go down 1, right 2. Down 1, right 2. Down 1, right 2. But because bless you, because I know that this should look like a V, you go in the other direction. Down 1, left 2. Down 1, left 2. So on and so forth. There is our graph. And notice how pretty wide it is. Well, it's because we're multiplying by a number smaller than 1 in magnitude. Sketching absolute value functions, pretty child's play when it comes to if you're going to use function transformations, right? Now, the reason why we listen to function transformations or study them is because, again, it can work with any old function. So I'm going to draw a pretty funky graph here. It's funky and to the point where I don't have an equation for it. It's just going to be random lines here. So suppose, just draw some tick marks here. And let's say you had a point at the origin, 0, 0. You had a point at 2, 3, and you had a point at 5, 3. So there's my graph. Right. It's not an absolute value function. It's not a linear function. It's just a composite function. So I tell you, this is the graph of y equals f of x. So that is our original picture. Here's the actual question. Letter A, sketch y equals 2 f of x. Letter B, sketch y equals negative f of x plus 2 plus 1. This seems like a what is going on type of problem. Well, to answer this question, all you have to do is to be able to read the transformations. So let's do letter A first. So I'll do a solution in different color. If you read this, right, tell me, just in layman's terms, you don't have to use fancy technical math jargon. What does this notation here tell you to do? What is it literally doing? It's doubling the function, right? It's multiplying by 2. Now, do you see here how the original definition, the original function is y, right? Y is literally the function. You said I was doubling the function. So what variable am I doubling? The y's. Guess how the graph of letter A will look? It'll look like the same picture, except the y's get doubled. That's it. So we can sketch them. So I'll go ahead and sketch them. And since my graph is nothing but line segments, I'm just going to focus on the points. Let's focus on the point 0, 0, the point 2, 3, the point 5, 3. Well, let's transform 0, 0 first. If y equals 2 f of x literally says double the y value, if I have 0, 0, and I double the y value, what's my new point? If I double 0, it still stays a 0, 0. Let's focus on the point 2, 3. All this says, remember, this says double the y value. It doesn't say anything about the x value. Y equals 2 f of x simply says double the y value. So if it's 2, 3 originally, my new point becomes 2, 6. My third point is 5, 3. This function says double the y value, so my new point becomes 5, 6. That is the graph of letter A. And notice how it's sort of taller, it's stretched up as to compare to the original, because you are literally stretching the y values. Okay. Let's do letter B. That's going to be a little bit trickier because you have lots of stuff going on. So just as before, just shout it out. Read it to me. What transformations do you see? I see up 1, left 2, there's one more. What does a negative, when you multiply a function by negative, do? It flips upside down. Now, function transformation follows orders of operations like regular numbers. In other words, we have to do multiplying and dividing first before we do adding and subtracting. So I hope everyone can see that the up 1 is done through addition. The left 2 is done through addition. The flip upside down is done through multiplication. So when I do function transformations, we have to do the flip first before we do the left and right motions. So let's see what the solution would look like here. And just so you don't have to, I don't have to constantly scroll up and down, the original points were 0, 0, 2, 3, 5, 3. Let's start with 0, 0. Okay, I'm at the origin, 0, 0. You guys can see that point, right? Barely. 0, 0. Flip it upside down. Where am I at? 0, 0 still. Then I move left 2, up 1. There's your new point. Now let's transform the point 2, 3. If I flip him upside down, where will he go? Here's the original point. So I'm going to erase it just so you guys can see it. Here's the original point. If I flip him upside down, where will he go? Positive 2, negative 3. So when you flip things upside down, the only thing that changes is the y value. So I'm now at 2, negative 3. It's at this point where I can go left, right, up, down. Left 2, up 1. There's my new point. And then let's transform 5, 3. If I'm at 5, 3, flip him upside down, he goes to 5, negative 3, and then at 5, negative 3, I'll go left 2, up 1, which brings me to 3, negative 2. That is our graph. Nope, there's no arrowheads because these are line segments. So these function transformations work more than just with absolute value functions. They work with every single function in mathematics. So for this lesson, we have two objectives. You should be able to sketch any linear absolute value function I give you, and you should be able to sketch really any function I give you by listening to function transformations. So that's what I want you guys to practice on with 2.8.